Hey everybody, welcome to another deep dive today. We're going to be looking at something that was suggested by senior technical writer Kurt Robbins.
Oh, cool.
He sent this in. He thought it would be interesting for, folks like, technical writers, documentation specialists, IT professionals, folks like that. And I think he's right.
Yeah, sounds right up our alley.
So we're going to be looking at some excerpts from an article called Visualizing the Turing Machine
Okay.
by Sam Rose. And you might be thinking, Turing machine, isn't that like a theoretical thing, from back in the day?
Yeah, like 1930s kind of thing, right?
Yeah, exactly, like 1936. So, before computers as we know them even existed.
Yeah, crazy.
But get this, the concepts that were, dreamt up, back then actually underpin the very devices that we're using right now to have this conversation, to record this, to, put it out there.
Wow, that's wild.
Yeah, it's really fascinating. So we're going to kind of unpack this a little bit, but just to kind of set the stage, picture a machine.
Okay.
It's got four parts.
All right.
It's got a tape, it's got a head, it's got a program or a set of instructions, and it's got a state.
Okay.
Sounds simple, right?
Yeah, deceptively simple.
So that's what's so cool about it. And we're going to kind of go on this little journey and see how this really simple concept revolutionized the field of computing.
I'm excited.
Yeah, me too. I was blown away when I was looking at the Turing machine simulations in Rose's article. It's really cool to see something so fundamental kind of like visualized
Yeah.
and really understand it.
Yeah, so what's really neat about the Turing machine is that it accomplishes so much with like so little.
Right,
Like you have these 5 basic instructions, you know, print a symbol on the tape, move right, move left, change to a different state, or just halt.
right.
And that's it. That's all it can do.
Okay, but wait a minute. Are you telling me that, like, everything can be computed with just those five things?
That's the idea.
Word processors and, like, YouTube and video games?
Yeah, theoretically, yes.
Really?
Yeah, that's the whole idea of computability.
Okay,
If there is an algorithm if there's a set of instructions to get you from some input to some output, then a Turing machine can do it.
okay. All right, that's impressive.
Yeah.
But okay, what about this infinite tape business? Because, my computer definitely does not have infinite memory.
Right.
So how does that work in reality?
Yeah, so that infinite tape is really a thought experiment. It's a theoretical concept.
Okay,
So it represents the idea that a Turing machine has access to unlimited memory.
okay.
Now, in real life, obviously, we have finite resources.
Right.
When we say something is Turing complete, what we mean is that it could theoretically simulate a Turing machine if it had access to infinite memory.
Okay, so, like, it's Turing complete enough for all practical
Indeed.
purposes.
And it all comes down to algorithms. A
Uh-huh.
Turing machine can execute any algorithm.
Okay, I'm starting to see how this connects. But okay, we're talking about, like, manipulating symbols on a tape. How do we get from that to, like, browsing the web? You know?
Right, so think about the building blocks of a modern computer. You've got the CPU, right?
Okay.
And it's got these things called registers,
Okay.
which are basically like tiny little super fast memory slots.
So registers are kind of like variables in
Right.
programming.
Precisely.
Okay.
They hold information while the CPU is working with it. And so here's the really interesting part. Those registers can be simulated on a Turing machine.
What?
Yeah.
Really?
Rose even shows in his article how to implement like the x86 instruction INC,
Okay.
which is basically just increment of value.
Right?
But he shows you how to do it with the Turing machine.
That's wild. But from what I've seen of Turing machine programming, it seems like incredibly tedious.
Oh, yeah.
Like to add two numbers together, you'd have to like write a novel.
Exactly. And that's not really the point of a Turing machine. It's not meant to be a practical computing device. It's really a theoretical tool to explore, the nature of computation itself.
So it's not about the speed, it's about
It's about the underlying concept.
concept.
Yeah.
Okay, and that concept is pretty powerful.
Yeah, it is.
Okay, but it's got to have some limits, right? I mean, like, what are the limitations of this thing?
Well, one of the most famous limitations is something called the halting problem.
Okay.
And what Turing proved was that there are some problems that no algorithm, no matter how clever, can solve.
Whoa.
Yeah, so that means that even with like all the amazing computing power we have today, there are some things that we just can't figure out.
That's kind of humbling.
It is, it is.
Okay, so we've got this theoretical machine that can compute anything that's computable,
Right,
but there's this catch, or this halting problem.
right.
So it's like there's this brick wall that even a Turing machine can't break through.
That's a good way to put it, yeah.
All right, so this concept of Turing completeness, I mean, this pops up in the most unexpected places. Like, who knew that Microsoft Excel could be Turing complete?
It's crazy, right?
Yeah, it really makes you think about, like, if something as simple as a spreadsheet can be Turing complete, then what are the implications of that for, like, technology in general?
Yeah, and the potential risks too.
Yeah, exactly. Like, what are the, where does that lead us?
Right.
But let's maybe kind of back up a little bit and, like, delve a bit deeper into, like, how the Turing machine itself actually works.
Okay.
Rose gives some really cool examples and simulations in his article that kind of help you visualize the whole process. I was really struck by the program that he shows for printing, like, alternating zeros and ones on the tape.
Oh, yeah, that's a classic example.
It's just like these two states, and it just keeps flipping back and forth between them.
Yeah, it's like this really elegant little dance between the states and the instructions.
And all this is happening on that infinite tape, right?
Yeah, the infinite tape is key because it's both the input and the output.
Okay.
Like, that's where the data is stored, and that's where the results of the computation are written.
So it's like the ultimate scratch pad.
Exactly, a scratch pad that can theoretically extend forever.
I love it, okay, but in Rose's article, he mentions that Turing liked to leave spaces between the symbols on the tape.
Oh, yeah, he called them F squares and E squares.
Okay, what's that all about?
It's a little quirk of history. I guess Turing imagined these squares as helping the machine keep track of where it was on the tape.
Okay.
So the F stood for figure, which represented the actual symbols,
Uh-huh.
and then the E stood for erasable, which was basically like a blank space that could be used for like temporary markers or, calculations.
It's amazing to think about, like, how much thought went into this, like, theoretical machine.
Yeah, and it's cool to be how he used those squares in his algorithms.
Yeah, it's like watching the birth of computer science.
Right.
But for me, the real, like, mind bender is this idea of computability. Like, how can we be sure that everything that is computable can be done by a Turing machine?
Right. It's a bold claim.
It is.
But the beauty of what Turing did is that he gave us a framework for defining what computable even means.
Okay.
He basically said if you can come up with a set of instructions, an algorithm to solve a problem, then a Turing machine can execute those instructions.
So it's not about the machine itself, it's about
It's about the logic behind it.
the
It's their
logic.
power of algorithms.
Okay, and that's why we see Turing completeness popping up in all these, like, weird, unexpected places.
Exactly.
Because if a system can simulate the logic of a Turing machine, then boom, it inherits that computational power.
It's like this hidden potential lurking everywhere.
It is okay, but there are limits, right? We talked about the halting problem. This is like,
Right.
even a Turing machine can't crack this nut. Wow. Okay, so we've got this theoretical machine. It can compute anything that's computable.
Right.
But how do we get from that to, like, the computers we use every day? How do we get from, like, manipulating symbols on a tape to, like, browsing the web and watching videos and all that stuff?
Yeah, that's where the ingenuity of computer engineers comes in, They've
Whoa.
taken the fundamental principles of the Turing machine and they've translated those into physical hardware and software.
So our computers are like supercharged Turing machines, basically.
In a sense, yes, they use these electronic circuits, memory complex software to carry out computations at like incredible speeds.
Right.
And while they don't have infinite tapes, their finite memory is vast enough to handle incredibly complex tasks.
But at the heart of it all, it's still about those algorithms, right?
Absolutely. Algorithms are the language of computation. And whether we're talking about a theoretical Turing machine or a modern supercomputer, it all comes down to those instructions.
Right. I'm starting to feel like I'm getting a grasp on this.
Good.
But I'm still a little fuzzy on how we get from these, like, simple operations like adding binary numbers
Right.
to the complexity of, like, modern software. I know Rose mentioned something about, like, simulating registers on a Turing machine.
Ah, yes. So remember we talked about registers and CPUs, those tiny little memory slots that hold values. Well, Rose actually shows how you can create virtual registers on a Turing machine
Okay.
just by like cleverly organizing the symbols on the tape.
So it's like dividing the tape up into, like, sections, each one representing a different register.
Exactly.
Okay.
And then you can write Turing machine programs that manipulate those virtual registers, just like a CPU manipulates its physical registers.
So wait, let me get this straight. We can simulate registers on a Turing machine.
Yep.
We can use those registers to do calculations just like a CPU.
Right.
And since a Turing machine can compute anything that's computable, that means theoretically we could run, like, any program on a Turing machine.
Theoretically, yes, it might take a really, really long time.
Right.
And you might need a tape longer than the universe.
Right.
But the logic is there.
That's mind-blowing.
It is. It really highlights the power of Turing's ideas.
So what's the takeaway here? Like, what's the so what of all this Turing machine stuff?
I think the main takeaway is that computation is fundamentally about algorithms.
Okay.
It's about those step-by-step instructions that can be executed by a machine, whether it's a theoretical Turing machine or a real-world computer.
And those algorithms are surprisingly powerful.
Yeah, they are.
They can solve a huge range of problems.
Right.
But they do have their limits.
They do, and the halting problem reminds us of that.
Well, listeners, we've reached the end of our deep dive into the world of Turing machines and Turing completeness. I hope you enjoyed the journey and that you learned some valuable insights that you can take with you.
Me too. It's been a great conversation.
Remember, the legacy of Alan Turing is all around us. It's in every line of code we write, every system we design, every problem we solve. So as we keep exploring new technological frontiers, let's keep Turing's vision in mind. His work reminds us that even the most abstract ideas can change the world. Thanks for joining us on this deep dive.